Okay. So the last time video was terrible. Maybe today I was capable to set up the high resolution camera. We will see what happened at the end of the class. But I think today is going to be better. I think you know that we have a homework that is due next week on Tuesday. And it covers 9.1, 9.4 that today we are going to finish. So on the board, I think what we already covered last time about section 9.2. Remember that we discussed 3D reference space. So we introduced the 3D reference system, which now has 3 axes. Y and Z are on the board. You have to think that X comes outside of the board. Any point P here in the space will have 3 coordinates, X, P, Y, P, Z, P. And this is a way to represent them. So you take P, you project it on the XY plane. What do you think are the coordinates of this projection? What do we lose here when you project on the XY plane? You lose Z, 0, right? So this is going to be the point XP, YP, 0. So you project P on the XY plane. This distance is exactly ZP. Then you take this point and you project it on the x-axis. So this is going to be the point XP, 0, 0. And this distance is exactly YP. And the intersection on the x-axis is exactly XP. Okay? So I did it in the order X, Y, Z, but you can change anymore. So we start looking at the reference plane. Z equal to 0 is the XY plane, where all the Z points have 0 coordinates. Y is equal to 0 is the XZ plane. So is this plane coming out of the board. Here is Y, that is 0, and X equal to 0 is the YZ plane. This is the whiteboard. Then, in order to get the reference axis, the x-axis, y-axis, z-axis, we made a system of equation between the reference plane. And the x-axis is the intersection between y is equal to 0 and z equal to 0 is the intersection between these 2 planes. And so this is how you represent the x-axis. In 3D, similarly, we have the y-axis and the z-axis as an intersection of the reference plane. Then we also saw horizontal planes. Z is equal to C is a horizontal plane whose z-intercept is C. Instead, y is equal to B and x equals to A. These x is equals to A are planes parallel to the whiteboard that intersect the x-axis at A. And y is equal to B are these vertical planes that intersect the y-axis at B. Finally, we look at the distance formula between 2 points P and Q, which was a generalization of the distance formula in 2D. So the distance is square root of xp minus yq square plus yp minus yq square plus zp minus zq square. And the middle point between P and Q, which is given by xp plus xq half, yp plus yq half, and zp plus zq half. Okay, any question on this? Everything clear? So let's start at looking at some equations. Remember, I told you last time that in calculus 1, an equation generally represents a curve. In calculus 3, an equation will represent a surface. So let's start. with what we call cylindrical surfaces. So I'm writing down an equation, we discuss it, and then we generalize. X squared plus y squared equals to 4. And I'm asking you, what is this equation? You should answer me, it depends if you are talking about 2D reference systems or 3D reference systems. So let's start in 2D. What is that?
Circle. That's radius.
This is just a circle centered at the origin with radius 2. Everybody should know this, right? So the center of this circle is at the origin, the radius is 2, so it's going to be something like this. So we are in the 2D reference system where we only have the x and the y coordinates, right? So this is an equation, a constraint between x and y. It means that this circle is basically all the points in the xy plane that satisfy this equation. Agree? So now I'm taking the same equation, but I'm saying, look, this is in 3D. So x squared plus y squared equals to 4 in 3D. So now think that this is the set of all the points x, y, z in the 3D space that satisfy this equation. Agree? Notice that z is missing. Right? So you can find just all the x, y that satisfy this equation and then put any z, because z is not in the constraint equation. Make sense? So how do we visualize this equation? We start with the z equal to 0 plane. So I'm saying, let's do a system of equations between our constraint equation and z equal to 0. I want to see what happens if I cut this surface, this equation, with the horizontal plane z equal to 0. What do you think is this equation? Now, it's a system between this equation and this other equation. It's the system between two surfaces. It's the intersection between two surfaces. What do you think is going to be this equation as equal to 0? It's going to be exactly the circle of radius 2, center at the origin, but placed on the xy plane as equal to 0. Does it make sense? Because the x and y on this circle will satisfy this equation. We know it from calculus 1. We don't. And then I can choose z equal to 0 because this equation is z independent. This constraint does not depend on z. Make sense? Similarly, I can say, let's see what happens when I slice this surface with a plane z equals to 1. What is the plane? We said that is a horizontal plane parallel to the floor with the intercept of 1. So on this plane, z equal to 1, we are satisfying exactly the same equation, which involves only x and y. So we are going to just get a shift of our circle as z equals to 1. Make sense? we can generalize this concept for any int is equal to c vertical horizontal plane. So if we take c, we are going to get what? Another circle with the same x and y, but z at c. And we can get that for any c, which means that we basically can take any of this circle and shift it parallel to z. What do we do if we take that circle and we shift it parallel to z? We are going to get a cylinder. It's going to go plus and minus infinity in z. So the cylinder never ends. So cylindrical surface. What is a cylindrical surface? A cylindrical surface is one equation in 3 dimensions where one or more than one unknown is missing. Okay, so we recognize that this is a cylindrical surface. Why? Because z is missing and we are in 3D. This is what? In 3D. Is a cylindrical surface, right? Why? Because in this equation, y is missing. What is this? Is a cylindrical surface. Why? Because x is missing. What is this? Is a cylindrical surface because both x and y are missing. Okay? So, as long as you are missing one or more variables, those are all cylindrical surfaces. Now, see, when we took this circle, we shifted how? Moving parallel to z. Why? Because this was missing. Same thing here. You are going to take this curve and shift it parallel to what? To y, because y is missing. So left to right. Here, parallel to x. Shifting back to front. Here, you can choose x or y. Okay? Okay, we are going to see these examples in a second, but let's focus again. So, the variable that is missing gives us the direction of shifting. What are we shifting? We are shifting this equation. Okay, we are shifting this equation, which we can get from what we know in calculus 2, or in calculus 1, in whatever, analytical geometry. So, we are looking at the trace of this surface in any plane. We choose z equal to 0 because it's simpler for us to visualize on the xy plane. Or it's going to be the y is equal to 0 plane or the x equal to 0 plane. So in one of these 2 planes, depending on what is missing. So here is missing z. We are going to check it on the xy plane. And then, so we sketch the trace, and then we shift the trace on the axis. Agree? So let's start with this one that is easier. What do you think we are going to get there? So this is a cylindrical surface that evolves parallel to x, right? On the YZ plane, what is the YZ plane? A whiteboard, right? What do we get? What is the trace of this equation on the YZ plane? It's a parabola, right? You can write as z equals 4 minus y squared. What is this parabola? In the YZ plane is a parabola with vertex at 4, which opens to the negative the axis. So the trace of this cylindrical surface on the YZ plane is that parabola. What do we do with this parabola to get our surface? We shift it parallel to x. So what we are going to get, let's do this first. Let me try to get it right. Something like this. Agree? Can you see it? So this is a cylindrical surface parallel to x, whose trace on the YZ plane is z equals 4 minus y squared. And we know how to sketch 4 minus y squared from analytic geometry. Any question? So this is a little bit more tricky. Who knows what is that? In 3D. Can you describe this surface? There is a cylindrical surface, right? Parallel to what? The evolution is going to be parallel to y. Whose trace on the xz plane is what? This is that equation. Hyperbola. Okay, so if you don't know the equation of the hyperbola, you should know it. But if you don't, we are going to review surfaces in 3D, which will involve a lot of this analytic geometry stuff. So you have plus, plus, minus, minus. What does it? So plus, minus, plus. What does it mean? That the two branches of the hyperbola will open to the positive and negative x-axis. We're going to see this in a couple of time lecture, but you should know these things. So if you sketch the asymptotes, so these are all the intersection 1, 1, negative 1. And you sketch your asymptotes. Then these hyperbolas will be this one and this one on the back dash. And then you are going to take these two branches of the hyperbolas and shift it front and back. Sorry, left and right, not front and back. So there is too much junk in the middle, so let me remove the junk in the middle. That is only needed to sketch our trace, but once we have the trace, it's probably better to remove it otherwise. So think this hyperbola is on the x plane, and then we are shifting it. So maybe something like this, where this is connected with this, and this is connected with this. I don't know if you can see. I can see. Except there are two sheets now, a front one and a back one. Okay? Now, z equals to 4. We already know that this is a horizontal plane. There is no mystery, but you can consider any horizontal plane to be also a cylindrical surface. For example, you're saying, okay, there, both x and y are missing, right? So I'm saying, okay, I'm going to consider x has the missing variable. So I'm going to start first on the yz plane. On the yz plane, which means the board, z equals to 4 is the horizontal line which intersect the z-axis at 4. And then I'm shifting this line parallel to x, and you get your cylindrical surface, your horizontal plane. Same things you can think if you consider this a cylinder that evolves parallel to y. In the x, z plane, you can fix z equals to 4, and then shift this left and right. Same thing, you're going to get your horizontal plane. Okay, so all of these equations where one or more variables are missing, we call them cylindrical surfaces. See, they are all surfaces, okay? They are not lines. You get the information of the trace on one of the reference planes by the constraint equation as you did in the past in that particular plane. Okay? Any question on that? Clear? So it's very important that we distinguish equations if we are in 2D or in 3D. Now, if you have the z variable, you immediately say, oh, I'm in 3D. But this example that we saw before is confusing. Okay, it should be very clear if we are talking about the 2D or 3D reference space. In 2D, this is a circle. In 3D, is a cylinder. Okay? Sphere of radius A and center in H, K, L, that's a script L. Okay, so what is the geometric definition of a sphere center at C and with radius A? Is the set of all the points whose distance from C is A. Agreed? So what's going to be the equation of the sphere that satisfies this geometric definition? Distance equals to A. What is the distance formula between any points x, y, z on the surface of the sphere and the center C of coordinate HKL. Distance formula, we say is the square root of what? Of the x-coordinate of this generic point minus the x-coordinate of the center. It's going to be x minus h squared plus the y-coordinate of this generic point minus the y-coordinate of the center, y minus k squared plus z minus l square. Agree? So this is the distance formula. We know that this distance should be equal to a positive number, clearly. So we don't like the square root on the left. What we do is that we square left-hand side and right-hand side, and we get our equation. Is x minus h squared plus y minus k squared plus z minus l squared equals a squared. So this is the standard formula for a sphere centered HKL with radius A. Agree? It comes straight forward from the definition of distance. So, what is the equation of the sphere of radius 3 centered at 1, 2, 3? Very simple. We already have all the information that are needed. We have the coordinate of the center. We have the radius. So it's going to be x minus h1 squared plus y minus k, y minus 2, everything squared, binomial square, plus z minus l minus 3 binomial square equals radius squared. That's it. Very simple. More complicated. I give you a quadratic equation and ask you to complete the squares in order to get the center and the radius of the sphere represented by that quadratic equation. So let's say we have something like x squared plus y squared plus z squared minus 6x minus 4y, let's put a plus for y, minus 7 equals to 0. So the problem says, find the center and the radius of the sphere represented by that quadratic equation. So why is a sphere? Because I wrote it in a way that is a sphere. Okay, I know how to do that. So I'm telling you, this is a sphere. Find the center and the radius. We're going to learn to distinguish what is not a quadratic, what quadratic equations are and what they represent. This one is the equation of the sphere. So, as you did in Calculus 1 analytical geometry, what you do is the procedure of completing the squares, right? So, what do you need to do? you need to group together all the x terms. You need to group together all the y terms. You need to group together all the z terms. There is only z squared. There is no linear term in z. And you send the constant on the right-hand side. So we basically what we do is that we manipulate this equation without changing it. So collect, 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 send the constant on the right-hand side. Okay, so we are looking for HKL. The information about HKL is going to come from the coefficient in front of the linear term. And it's basically H in X. You're looking at the X terms. You are going to collect -6, the coefficient in front to X, and divide it by -2. So we get 3. Here, you are going to add H squared, 9. Now, some of you does not divide by -2, divides only by 2. But this is not going to give you H, it's going to give you negative H. So since I want to see H, I divide by -2. It doesn't matter because then we are going to square it. So if you square the negative H or H squared, you get exactly the same number. But since I want to know who is H, I'm dividing by -2. Similarly, here you get a K coefficient by taking the coefficient in front of Y divided by -2. So K is going to be -2. You add K squared. So you have -2 squared. And the coefficient in front of the linear term of z, I wrote it down, but is 0. Right? So 0 divided by -2 is 0. So there is no really need to do anything. And now we need to be careful that we are manipulating an equation. We don't have to change the equation, right? So what we do, what we added on the left-hand side, we are going to add on the right-hand side. So here, better that I write this one. So 9 plus 4. Okay? So again, it's a manipulation of the same equation. The equation did not change. It satisfies exactly the same point as before. So what's going to be this? Is going to be the square of the binomial x minus h. It's going to be x minus -2 square plus y minus k. Sorry, this is 3. I move to the other. X minus h. So it's going to be x minus 3 square plus y minus k, y minus -2 square plus z minus 0 square, z square, equals to, what is that, 11, 18. So you can rewrite 18 as 9 times 2, so 3 square, radical 2 square. So you can rewrite 18 as 3 radical 2 square. Right? Because it's 9 times 2, 18. So, what is the center of our sphere, HKL? 3, -2, 0. What is the radius? 3, radical 2. Okay, I did a terrible mistake. Sorry, I see the faces. You should stop me if I do a mistake. There is so that's 20. So square root of 20 is to radical 5. So the center of the sphere is in 3, negative 2, 0, and the radius is 2 radical 5. Now, this procedure of completing the square was simplified a lot because we had all ones in front of the quadratic terms, but in general can be more sophisticated. We are going to see a more sophisticated approach later. For now, but you already know that. So here I'm still inside. Any question? Pretty clear? So we are seeing two family of surfaces, cylindrical surfaces and sphere. For now, we stop with the surfaces. We introduce vectors in 3D. So when we introduced vectors last time, remember we were in the 2D reference plane, so we were on the board. Now our vectors are in the 3D reference space, so a vector which I don't have other way than sketch it exactly like it was last time. You have to figure this vector now is coming out of the board. So I'm going to put it here in 3D. Okay, so those are not vectors on the whiteboard. They are 3D vectors. Okay, so geometrically nothing changed. Okay, so all that we defined last time geometrically is exactly the same. So we jump immediately to the algebraic representation of vectors in 3D. And as we did it last time, we first introduced three vectors of length 1, parallel to the x-axis, y-axis, and now there is also the third one, the axis. So it's going to be the unit vector I, j, k. Then we take this vector b and we place it so that this foot is at the origin and this head ends at P. This point P is coordinate xp, yp, zp. So, as we did before, I can take this point P and project it on the xy plane. Then take this point here and project it on the x-axis. And I'm going to build the vector V as the sum of three vectors already also. All right. So I'm starting from the origin, and I'm going to have a vector parallel to the x-axis with length xp. Then from this point, I'm going to add a vector parallel to the y-axis with length yp. And then from this point, I'm going to add a vector with length zp parallel to z. So if I call this vector A, this vector B, and this vector C, our vector B is going to be the sum of A plus B plus C. for exactly the same rules that we saw last time. Put head, put head. Now, what is A? A is a vector parallel to I with length xp. So it's going to be xp I. B is a vector parallel to J with length yp. C is going to be a vector with length zp parallel to K. Since these vectors I, J, K are all unit, we can get those exactly. So this is the algebraic representation of our vector V. We can use again the angle bracket notation, which is open angle bracket, yp comma xp yp zp close angle. Okay. So why do we like the algebraic representation again? Because then we can do all the operation on these vectors in a very straightforward and simple way. For example, what's going to be the magnitude of the vector V? It's going to be the distance between the origin and the point P, right? So distance formula is going to be the square root of xp minus 0 binomial square, because the origin is coordinate 0, 0, 0, plus yp minus 0 square plus zp minus 0 square. So it's the square root of x squared plus y squared plus z squared. What's going to be the scalar multiplication by n of vector V? Is going to be n, which multiplies the vector xp yp zp. So you distribute the constant inside. So it's going to be the vector with components and xp and yp and zp, exactly as we did in 2D, but we have the third component. What's going to be V plus W vector? Now I'm going to write V is, now I'm going to write V1, V2, V3 to distinguish from W1, W2, W3 vector. So we are adding up the two vectors with components V1, V2, V3, W1, W2, W3. So this is going to be the vector, because x component is V1 plus W1, V2 plus W2, V3 plus W3. Okay. And you can combine scalar multiplication and addition as you wish. This n, remember, can be positive and negative. If it's negative, it's going to have opposite direction. So, as an example, let's evaluate. Let's do like we did last time, but now in 3D. Evaluate the length of V plus W let me put, sorry, 2b minus 3w, so let's complicate it a little bit, where v is the vector 1, 2, 4, and w is the vector negative 2, 1, 5. Okay, so again, you can try to do this in one shot, or better, we do it step by step. So what we can do is to first evaluate the vector 2b. What do? We take 2 and we multiply the vector 1 to 4. So we distribute the 2 inside. It's going to be 2, 4, 8. Then we can evaluate negative 3w. So we multiply the vector w times negative 3. So we distribute negative 3 inside w. So in this case, it's going to be 6, negative 3, negative 15. So then we add up to w plus negative 3w. So what we do is we add the x component, the y components, and the z components of these two vectors that we already evaluated. So it's going to be 2 plus 6, 4 plus negative 3, and 8 plus negative 15. So it's going to be the vector 8, 1, negative 7. And then we evaluate the length of this vector as the square root of the first component square plus the second component square plus the third component square. So this is 64 plus 1 plus 49. So it's 64 plus 50 square root of 114. Okay. Any question on this? So with this, we finish 9.2. So we take a break 10 minutes and we are going to restart at 12:30.
Sorry. It was, I don't think that they could clean up 20 years. They're completely destitute tonight. Clean.
Wonderful. We didn't even do anything. Our control on us.
So in section 9.3 and 9.4, you discuss the concept of dot and cross product between two vectors. I also call them, everybody calls them scalar or vector products. So let's start with the dot product. We have two vectors, A and B. Dot product dot B is equal to the size of A times the size of B times the cosine of the angle theta, where this angle theta is the smallest angle between the two vectors A and B when they have the same input. So if this is A and this is B, the first things that you do is that you place A and B exactly with the same input. So you shift them. So this point is the same. Then there are two angles here. Either this angle theta or the other one. But we always take the smallest angle. So this theta is always between 0 and pi. 0 when the two vectors are parallel, pi when these two vectors are antiparallel. Now, notice that I'm not doing any assumption about this vector. They are in 2D and 3D. Once this construction can be done for any vector in 2D and 3D. The only thing is that this plane where these two vectors are can be a plane that is not a whiteboard, it's a plane that is in the 3D space. Okay? So this is the geometric definition between of the dot product between two vectors. The result is a scalar, is a number, positive or negative, but it's just a number. So for that we say dot product or scalar product. Now, let's start making some distinction. So assume that A is parallel to B. A dot B is going to be what? It's going to be the size of A times the size of B times cosine of theta. In this case, if they are parallel, it means what? The theta is 0, right? When the two, this vector A and this vector B are parallel, there is no angle between them, or angle 0. So these are going to be just the size of A times the size of B times the cosine of 0, which is 1. Let's go to the other extreme. A is anti-parallel to B, so theta is pi. So in this case, A dot B is equal to the size of A times the size of B times cosine of pi, which is negative 1. So in this case, it's going to be negative A size times B size. So these are the two extrema. Theta is equal to 0, the two vectors are parallel. Theta is equal to pi, the two vectors are anti-parallel. So let's go in the middle. A is perpendicular to B. A and B are 90 degrees. In this case, the dot product A dot B is going to be the size of A times the size of B times the cosine of pi over 2, but this is 0. So when two vectors are 90 degrees to each other, their dot product is always 0. Okay? Now, let me write it here. If theta is strictly less than pi over 2, A dot B is going to be the size of A times the size of B times cosine of theta, but in this range, the cosine is positive. So the dot product is going to be strictly greater than 0. And for pi over 2, strictly less than theta, strictly less equal than pi, again, this product is going to be same definition, but in this range, the cosine is negative. Clearly, the length of A and the length of B should be different from 0. So all I said until here has a condition that if A is different from the 0 vector and B is different from the 0 vector, because otherwise you always get a 0, no matter what. Okay? Because either the size of A and the size of B are equal to 0. Okay, so this is the geometric definition of dot product. Now, if the vector A is equal to A1, A2, A3 vectors, and the vector B is equal to B1, B2, B3 vector, algebraically, you can prove that the dot product A dot B is equal to A1, B1, so the product between the x components of the two vectors, plus B1 times B2, A2 times B2, the product between the y components of the two vectors, plus A3, B3, the product between the z components of the two vectors. Okay, so it can be proved that this geometric definition is equivalent to this algebraic definition. However, we like this definition very much because it's very easy to compute. This is not that easy. We will need to get the length of A, measure the length of A, measure the length of B, measure the angle, find the cosine of that angle. That's very hard work from a geometric point of view. And also very precise. This is very precise and very simple to compute. However, since we have this identity, there is some information that we can use, geometric confirmation that we can extract by this identity. We are going to see a couple of problems. So let A be 2, 1, 4, and B equals to negative 1, 3, 7. Find the dot product A dot B. So this is very simple. We have our geometric definition, algebraic definition of dot product. So what we do is we take 2 times negative 1 plus 1 times 3 plus 4 times 7. So we just apply this formula here straightforward. And so it's going to be negative 2 plus 3 plus 28. So it's going to be, what is this? 29. Okay, so the dot product, once we have the two vectors, it's very easy. You just do use the algebraic definition. Now, same vectors, I'm asking you to find the angle theta. Or let's start to say find, okay, let's say find theta between A and B. Let me write it here so we still have space. Find theta between A and B. So we want to find the angle theta, the smallest angle between these two vectors. So we have that geometric definition that says that A dot B is equal to the length of A times the length of B times the cosine of theta, which means that cosine of theta is equal to A dot B divided by A B, A length, so divided by A length times B length. Agree? So once you get this number, theta is going to be cosine inverse of that number. Make sense? So we already evaluate the dot product A dot B is 30. We need to find what is the length of A and the length of B. So the length of A is going to be the square root of 2 square plus 1 square plus 4 square. So square root of 2 square is component, what component? The component square. So it's going to be 16, 17, 21. Square root of 21. The length is going to be the square root. Now we're going to have negative 1 square plus 3 square plus 7 square. So this is 49 plus 1, 50 plus 9, 59. Square root of 59. So we can go here, say cosine of theta is equal to 29 divided by square root of 21 times square root of 59. And then theta is going to be cosine inverse of this number here. There is not too much to simplify. So it's going to be 29 divided by square root of 21 times 59. Of course, this is going to be some number. You can plug it in the calculator and get your angle. Okay, or just leave it like this, where work will accept answers like this one. Now, what is the range of cosine inverse? Remember that cosine inverse, what are the output angles? From 0 to pi, right? So the output of this function is in line with the domain of theta. Okay? So this is perfectly fine. If the dot product is positive, you're going to get an angle between 0 and pi over 2. If the dot product is negative, you're going to get an angle between pi over 2 and pi. So, if you want to know the cosine, straightforward, you can use this formula. If I want to know the angle, from this formula, you get cosine inverse. Why I'm telling that? Because when we're going to do the cross product, something is not going to work. Okay? So, dot product, it's good to get the angle. Cross product is not, and we will see why. Okay? So remember that. Sorry, let me shut down. Okay. Any questions here? Remember this, right? So, with the dot product, we have also two other definitions, which are the scalar projection and the vector projection. Okay? Give me just a second. A dot B is equal to B dot A. So this product is commutative. Okay? Important. How do you prove that? B dot A, by the definition that we use here, is just going to be B1A1 plus B2A2 plus B3A3. But since each of these multiplication is commutative, you can reverse them and get exactly this definition here. It looks trivial, it is trivial, but the dot product is commutative. Okay? Any question on this? So, assume that you have two vectors, A and B. Let me place them already with the same foot. Again, this can be done in the 3D vector space. I'm going to do it in the 2D because it's a little bit simpler for me geometrically. I'm taking the head of A and projecting it on the vector B. We call the scalar projection of A over B this length, and is a length with sign, scalar projection. So this length is going to be positive if when you project it, this point is going to point in the same direction of B from the foot. It's going to be negative if when you project it, it points in the different opposite direction. So this is going to, the scalar projection here is going to be negative. So basically, this angle theta is less than pi over 2, the scalar projection is positive, and is greater than pi over 2, the scalar projection is negative. So the scalar projection is a length with sign. So scalar projection of A on B. So we are projecting A on B. So since this is a right triangle and this is the angle theta, you should agree that this is equal to A projection cosine of theta. Now, cosine is positive between 0 and pi over 2, negative for theta greater than pi over 2 and less than pi. So you see this definition of scalar projection gets exactly the right sign. Okay, positive or negative if theta is less or greater than pi over 2. 0 if it is exactly pi over 2. So, what is cosine of theta? What we wrote there, this is going to be equal to A dot B divided by the size of A, size of B. So the size of A and the size of A simplified, we get A dot B divided by B. So the scalar projection of A over B is going to be the dot product A dot B divided by the length of B. Where this formula makes sense? Only if B is not a zero vector. Okay, so be different of the zero vector. Otherwise, that definition doesn't make sense. You're going to get the 0 over 0, but there is no such a thing as a projection on the zero vector. The vector where you project should be different. Okay? The numerator is defined if b is equal to 0, it's just 0, but the denominator is not, so you cannot. And then the vector projection of A over B is a vector that is parallel or antiparallel with B, and in particularly is going to be parallel and equal to the absolute value of the scalar projection if the scalar projection is positive, and is going to be antiparallel to B with length equal to the absolute value of the scalar projection if theta is greater than pi over 2. So this is the green, red one is the vector projection, dt. So vector projection of A over B. So dt A on B. So it's going to be A dot B divided by the length of B. So this is going to give us the scalar projection, which has a sign positive or negative, times a unit vector B divided by B. So this vector is a unit vector always parallel to B. Okay? So notice, this always points in the direction of B as size 1. This is the length with sign of this vector. What does it mean? That it is equal to the scalar projection, right? This is the scalar projection. So this vector will have the length of the scalar projection, will point with B or negative B, depending on the sign of the scalar projection. So it's exactly this object. So this is equal to A dot B divided by the length of B squared, B. Now, clearly, you can see immediately by definition that this operation is not commutative. The projection of B on A will have A as the denominator. The vector projection of B on A is going to have a vector A here and the length of A squared as the denominator. So this operation does not commute. Okay? So find the scalar projection and the vector projection of A on B, where A is the vector 1, 3, 4, and B is the vector 2, 4, 3. So we want to find the scalar and the vector projection of A into B. So the scalar projection, we said, is going to be the dot product A dot B divided by the length of B. So we go here and say, what is A dot B? A dot B is obtained by doing the product of the x components 1 times 2, plus the product of the y components, 3 times 4, plus the product of the z components, 4 times 3. So it's going to be 2 plus 12 plus 12, 26. The length of B is going to be the square root of 2 square plus 4 square plus 3 square. So it's 16, 25, 29. So the scalar projection of A over B is going to be 26 over square root of 29. The vector projection is equal to the scalar projection times B over its length. So it's going to be the number that we just got, 26 over square root of 29, times B, which is 2, 4, 3, divided by another square root of 29. So if you want, 26 over 29 times the vector 2, 4, 3, for square root and square root, simplify. Okay? Any question? Everything clear? Let A equal to 1, 2, 3, and B equal to 2, 2, 2, 2, 2, 2. Let me do the math in my head. Say 3. -3. Verify if A is orthogonal to B. So, what is the test that we do? A and B are orthogonal to each other. What is their dot product? Need to verify if this guy is equal to 0. Right? This is the condition that two vectors are 90 degrees to each other. So let's try. I did it correctly. We should get a 0. So it's going to be 1 times 3 plus 2 times 3 plus 3 times -3. So we have 3 plus 6 minus 9 is 0. So the two vectors are orthogonal to each other. Verify if A equals to 2, -3, 4 is parallel or antiparallel to B. let's say it's going to be -4, 6, -8. And here, I want to verify if two vectors are parallel or antiparallel. Yes.
You multiply it by a constant, see if they're the same.
Yeah, that's gonna come later. That's the best way. But you're perfectly right. So I give you the wrong way to do it to see that it's very expensive, and then you use your method, which is much simpler. So we check with the dot product that if A is parallel to B, then A dot B is equal to the size of A times the size of B times the cosine of 0, which is 1. And if A is antiparallel to B, then A dot B is equal to minus the length of A times the length of B, because cosine of phi is -1. So if you want to put this together, you can say that A is parallel or antiparallel to B if the absolute value A dot B is equal to the length of A times the length of B. Okay, so the right hand side is always positive, so you need something to make the left hand side positive, the absolute value A dot B. Okay? Make sense? So we can do this job. It's going to be not too complicated, but a long process. So let's see, what is A dot B? It's going to be 2 times -4 plus -3 times 6 plus 4 times -8. So it's going to be -8 minus 18 minus 32. So -40, -58. Then we look at the length of A. The length of A is the square root of 2 squared plus -3 squared plus 4 squared. So again, this is 16, 25, 29 square root. And if we do B lengths, we are going to get -4 squared plus 6 squared plus -8 squared. So this is going to be 64 plus 36, 100 plus 16, square root of 116. So square root of, so now we have to check if the absolute value of A dot B, which is equal to the absolute value of -58, is equal, I put a check, to the square root of 29 times the square root of 116. So if I did this correctly, this is nothing else than 29 times 4 times 29. So this is like 2 times 29, which is 50. 116 is 4 times 29. So you see that we got that the absolute value of negative 58 is equal to this product. So this is true. It means that the two vectors are anti-parallel because we have to change the sign of the dot product. Make sense? So this implies, let's put a minus, that A and B are anti-parallel. Okay, so you see, it requires a lot of work, not difficult, but some algebra, and then we can make easily mistake there. Your friend has a much better way than this. What is the way that he's telling us? Last time, we said that M dot A is a vector that is always parallel or anti-parallel to A. Agree? Parallel if this constant M is positive, anti-parallel if that constant M is negative. So when we want to check if two vectors are parallel or anti-parallel, B is parallel or anti-parallel to A if B can be expressed as the product between a constant M times A. Say that A is parallel or anti-parallel to B if A can be expressed as a constant, different constant, 1 over N of B, okay? So this is what I want to do, and in particular, I see that these coefficients are larger than these coefficients. So I'm going to figure it out if I can express the vector B as a scalar multiple of the vector A. How do I do that? So I put the vector B here, and I write -4, 6, -8. And a vector A here, which is, what is A? 2, -3, 4. And then I'm dividing, so it's like a division of these two vectors. There is no such a thing as an operation as the division to the vector. What I want to do is to divide the coefficients in X, the coefficient in Y, the coefficient in C, in Z, and see if I always get the same constant. If yes, then that's the constant M that I'm looking for. If not, the two vectors are not neither parallel or anti-parallel. But in this case, see, when you do this division, what do you get? Okay. Doesn't make sense what I'm doing. Let me put here. So I divide this -4 divided by 2. What do you get? -2. 6 divided by -3. What do you get? -2. -8 divided by 4. -2. Yes, I always get the same coefficient, -2. It means that B can be expressed of -2 times A. 2, -3, 4. So basically, instead of distributing the 2 inside, I'm collecting, I'm extracting a -2 from each component of B. So is equal -2 A, which means that the two vectors are anti-parallel. Okay, so this test is much simpler. It works if the two vectors are parallel, anti-parallel, or neither. If you get different numbers, then they are not parallel or anti-parallel. So the dot product is a good test to get if two vectors are orthogonal to each other is the best test. It's not a good test to get if two vectors are parallel or anti-parallel. Okay? Any question on this? So 9.4, we studied the cross product and or vector product. So in this case, we call it vector product because the result is always a vector. It's not a number, it's not a scalar, as before, as the dot product is a vector, it's a different vector. The dot product makes sense also for 2D vectors. You just drop one of the third components. The cross product makes sense only in 3D. Okay? So this is the generic definition. Geometric definition. So we have two vectors, A and B, and already placed them with the same foot. These two vectors are not on the board, are in the space. Okay? Theta is the angle between the two vectors. And for now, we assume that they are not parallel. Okay? So since they are not parallel, two vectors uniquely identify a plane. If they are parallel, this uniqueness disappears. Okay? So, since we have a plane, then we can define a line which is orthogonal to the plane. And sorry, I didn't tell you, what we are looking for is A cross B. So A cross B is a vector where the size is given by the size of A times the size of B times now the sine of the angle theta, which is again the angle, the smallest angle between A and B. And now I always give a direction to this theta, because I'm doing the cross product from A to B. So I'm going from the vector A to the vector B, so the angle has an orientation. Now, its cross product has this sign, is uniquely identified by those numbers, and also has a direction. The direction is given by this line. It's an oriented line, oriented with the right-hand rule, which is take your right hand and close it how theta is moving. So in this case, you see you're going from A to B. The times gives you the direction of this line. Okay, so again, A cross B is a vector whose size is given by this product, A length, B length, sine of theta. And the direction is given by this orthogonal line. This is a line which is 90 degrees with a plane. And is oriented according to the right-hand rule. Okay? Now, first things, B cross A. When we do B cross A, what changes? Not the length. Length is exactly the same. But not the plane. The plane is the same. And now theta, let's call it differently, phi, is going to be the angle that goes from B to A. So it's oriented the opposite way. So now, if you do the same trick with your right hand, you're going to go now from B to A and is going to point down. So B cross A is equal to minus A cross B. So this property means it's anti-commutative. If you reverse the order, you have to change the sign. Okay, so the dot product is commutative. The cross product is anti-commutative. Okay? Any question on this? So we have a geometric way to get our cross product. But we don't like geometric ways, we like algebraic ways. And again, it can be proved that if you have a vector A of components A1, A2, A3, and a vector B of components B1, B2, B3, A cross B is the determinant of the 3 by 3 matrix, where on the first row you have I, J, K, the unit vector parallel to X, Y, Z. On the second row, you have the components of the first vector, A1, A2, A3, and on the third row, you have B1, B2, B3. So this is a 3 by 3 matrix. We want to find the determinant of this 3 by 3 matrix. So the determinant of a 3 by 3 matrix is going to be the element, first row, first column, times the determinant of the 2 by 2 matrix obtained by removing this column, this row. So it's going to be I, which multiplies the determinant of the minor. This is called a minor, A2, A3, B2, B3. Then you move to the second entry of the first row, but you need to change the sign. So it's going to be minus J, which multiplies, you need to remove the first row and the second column where J is located, the determinant of the minor, A1, A3, B1, B3. So it means I'm taking this and that because I dropped this row where J lives and this column where J lives. Okay? Plus K, the third element of the first row. And now if I remove the row and the J and the column of K, I'm left with the minor A1, A2, B1, B2. A1, A2, B1, B2. For a 2 by 2 matrix, the determinant is always the product of the main diagonal minus the product of the other diagonal. So it's going to be I, which multiplies A2, B3 minus A3, B2, minus J, again, product, the determinant of this minor, A1, B3 minus A3, B1, plus K, which multiplies A1, B2 minus A2, B1. Okay? So this is the first and the last time that I tell you how to do the determinant of a 3 by 3 matrix. We're never gonna do that. Okay? We look at the matrix, we say I times the determinant of this minus j times minus j times the determinant of this minus plus k times the determinant of that minus. And we do most of this computation in our head. Okay, at least I do it. If you cannot, you have to write it down. Okay, but it's going to take too long. So let's do immediately an example. What is A? It's going to be the vector 2, negative 1, 3. Vector B is going to be 4, 3, negative 2. What is A cross B? A cross B is going to be the determinant of the matrix IJK times 2, sorry, on the second row, 2, negative 1, 3. Third row, 4, 3, negative 2. So we need to find the determinant of the matrix. On the first row, we put IJK. Second row, A. Third row, B. And so it's going to be I, which multiplies the determinant of this minor. What is that? Negative 1 times negative 2 minus 3 times 3 minus j, which multiplies the determinant of the matrix when you drop the row and column of j. So it's going to be 2 times negative 2 minus 3 times 4 plus k, which multiplies 2 times 3 minus negative 1 times 4. Okay, so this is going to be equal to, I'm going to the angle bracket notation because it's the one that I like it most. 2 minus 9, so negative 7. So we have negative 4 minus 12, negative 16, but we have a minus in front of everything. So plus 16. And then we have 6 plus 4, 10. And this is our cross product. Okay. Is it clear? So now assume that I'm asking you to find the sine of theta between the two vectors, A and B. Then this formula, assuming that both vectors are different from the zero vector, we are going to have the sine of theta is going to be the length of A cross B divided the length of A, length of B. This formula is perfectly fine. Then I'm asking you, find theta. And you said, oh, I already have sine theta. I'm going to say that theta is sine inverse of A cross B divided by A length B length. What's the problem here? So sine inverse, the range of sine inverse is what? Negative pi over 2, pi over 2. Agree? So it's not in the same domain of theta. So already that should be strange. But that say, okay, who cares? I'm gonna get a negative theta, I'm gonna add pi, I'm gonna get the theta that I need. Right? Wrong. Why? Look at this argument. This argument is always positive because it's a length divided by two lengths. Or let's say different from non-negative. The cross product can be the zero vector. So, as an answer of this object, you're always gonna get start from 0 to pi over 2. No matter. Even if your theta is greater than pi over 2, you're not going to get negative 1. You always are going to get this because the argument is always positive. So it's possible, not all the time, that you don't get the right angle. Okay, I see. This means inside, in. It's a mathematical symbol for in. The output of that sine inverse, since this argument is going to be always positive, it's going to always be between 0 and pi over 2. So you're never going to find from that problem a theta that is greater than pi over 2. Okay? So you never use this formula to get theta. Because if the two vectors points not antiparallel, but the two vectors are an angle that are obtuse, you're not going to get the right angle. You're going to get the corresponding acute one that has the same sign. Okay? So be very careful. If I ask you to get the sine, this is good. If I ask you to get the cosine, you use the dot product. If I'm asking you to get the angle, you always use the dot product, and from the dot product, you get the cosine inverse. Okay? What else? Let's say some useful application. Oh, before the application, let's see some property that maybe is going to be useful. Theta, okay. A and B different from the zero vector. So neither of A and B are equal to the zero vector. Theta equal to 0. What's going to be A cross B? The size of this vector will involve the sign of 0, right? What is sign of 0? 0. So if this is the case where A and B are parallel, sign of 0 is 0, this is going to be the 0 vector. So each component of that cross product is going to be identically 0. If A is anti-parallel, then again theta is going to be pi, sine of pi is 0 again, so A cross B is going to be again the 0 vector. If A is orthogonal to B, theta is equal to pi over 2. Now, this A cross B length is going to be the length of A times the length of B. Because you're going to get the sine of pi over 2, which is 1. Now, yeah, these are properties that you can use to check if two vectors are parallel, two vectors are antiparallel, or two vectors are orthogonal to each other. However, I prefer computationally this test to see if two vectors are orthogonal to each other. It's much simpler than evaluating the cross product. And I prefer this test to check if the two vectors are parallel or antiparallel. Okay? So don't use this because evaluating the cross product requires some work and sometimes some algebraic mistake. These tests are much simpler. Okay, but this property holds. So assume that I have 3 points in the space, a point A, a point B, and a point C. So these are 3 points in the 3D space. If they are not aligned, they define a triangle. This triangle doesn't have to be on the whiteboard. It can be coming out of the whiteboard. So I want to find a formula for the area of this triangle. So it's useful to use the cross product. Once you have the coordinates of A, B, C, you can define two vectors A, C, and B. Then the height of this triangle, let's call H the height of this triangle, B the base of this triangle. We know that the area is going to be 1/2 B times H. Now, what is B? B is the length of the vector B. H, you can think is the length of A times the sine of theta. Because that's the right triangle, right? Which means this is just the cross product length. So it's A cross B. Agree? This is just the definition of the length of this cross product. So we can define the vector A, we can define the vector B, evaluate the cross product, and I missed the 1/2. So there is a 1/2. And get the area using this formula. Okay. Now, I'm just giving you an example, and then we stop. Find the area. of the triangle. With vertices A, 1, 2, 3, B, 2, 4, 5, and C, 3, 4, 7. Okay, so these are 3 points in the space. The vector A is a vector that goes from A to B. So we get this vector by subtracting the components of B minus the components of A. So it's going to be 2 minus 1, 4 minus 2, 5 minus 3. So this is going to be 1, 2, 2. The vector B is the vector with foot in A and head in C. So similarly, we do 3 minus 1, 4 minus 2, 7 minus 3. So we are going to get the vector 2, 2, 4. 4, 2, 2, 4. 1, 2, 2. Okay. Then we can evaluate A cross B, which is the determinant of the matrix AJK. 1, 2, 2, 2, 2, 4. So it's going to be I, which multiplies A minus 4 minus J multiplies 4 minus 4 plus K that multiplies 2 minus 4. So it's the vector with components 4, 0, -2. So the area is going to be 1/2 the length of this vector. So it's going to be 1/2 square root of 4 square plus 0 square plus -2 square. So 1/2 square root of 16 plus 4, 20 square root of 5. You can collect the 2 out of the square root of 20. Okay? So this is just an application of cross product. So with this, we finish the review from 9.1, 9.4. So the homework is due on Tuesday over this topic, but it's a long homework. It's probably 29 problems, something like that. It's a long homework, but it's something that you should already know any covers for sections. So for that reason, it's kind of long. Any questions? So on Thursday, we start the new material, which is 9.5 parametric equation. So class is dismissed.